Hello, in this video we're going to talk about enthalpy. But before we talk about enthalpy, we need to go back a step and go back to the total internal energy change of the system. So delta U equals Q plus W. So now let's envision two scenarios. So in the first scenario, volume is held constant. And so if we just take this equation and rewrite it over here, but then we're going to put a little subscript on Q, V, for constant volume. So that's what this means. We're prescribing the path that the heat transfer takes by saying it's at constant volume. Now, since it's at constant volume, that means delta V is 0, and that means this whole term right here just drops out. So you're left with the change in internal energy is equal to the heat at constant volume. Now that's useful, so if you want to measure experimentally the total internal energy change for a system, which is a good marker of what's going on with your chemistry, all you have to do is run your reaction with a constant volume, and then the heat that comes out of that reaction is related to total energy. That's useful. Alright, so now the second scenario, and this is going to get us towards enthalpy. The pressure is held constant. So let's take the same equation again. And let's say delta U equals Q minus P delta V. And now we're going to say QP for heat at constant pressure. So then let's just rearrange this equation and we're going to solve for heat at constant pressure. So we'll just scoot this down here and rearrange it. So now we can't make a big simplifying step like we did on the last slide. So instead we're going to do something different. We're going to define a new function. So we define a function, enthalpy. And we say enthalpy is equal to total energy plus pressure times volume. Now, if you want to think about the change in enthalpy, which is the thing that we could maybe more likely measure, change in enthalpy equals change in internal energy times the change in pressure times volume. Now, if you're at constant pressure, that means you can take this pressure and factor it out of the final minus initial that the delta symbolizes, and then we're left with P delta V. So at constant pressure, you can write this equation, and therefore, by defining enthalpy in this way, we can say that the change in enthalpy is equal to the heat at constant pressure. So this is almost like cheating. It's valid and totally mathematically sound, but it feels like cheating in a way. Like, we're just going to define a new function so we can set the heat at constant pressure equal to some thermodynamic function. But it works. And most of the time when you're doing reactions, you're doing them in a room atmosphere where the pressure isn't really changing at all. So then the heat that you measure in these processes, it's nice to have it equal to some state function. So speaking of the state function bit, both internal energy and enthalpy are state functions that matter just on the final or the initial state and not how you get there. But Q is an energy transfer or a path function that depends on how you get there. So how can we make these equal? Well, by setting conditions on heat, either constant volume or constant pressure, this path is defined, and thus you can make the two equal to each other. So that works out. Okay, so like I said, most reactions are run at constant pressure, so enthalpy is very applicable. Now, if you have something that goes from reactants to products, since enthalpy is a state function, the change in enthalpy can be listed as just final minus initial. So, remember your products are going to be your final state, and your reactants are your initial. Granted, this is only true at constant pressure. Alright, so something else here is this degree symbol, which is the symbol that refers to a standard state, which is listed as a pure compound at a pressure of 1 bar or 1 molar. So if it's a solid, liquid, or gas, there's 1 bar of pressure of either the gas itself or of atmosphere over your solid or liquid. And if it's an aqueous solution, or really any solution, you have a 1 molar concentration. So why do we have a standard state? Well, enthalpy values are going to change slightly between reactions at different constant pressures. And so if you want to have a value that you can list in a book for the enthalpy change of some reaction, you need to define what pressure you're operating at. And so just by putting this little degree symbol in here, we define that we're at a pressure of 1 bar, and then that's a nice easy number to compare with other enthalpy values you can see listed. So that's what we do with the degree symbol. Okay, so that's enthalpy. So what do we do with this? So I'll give a couple examples. And these are called thermochemical equations, these examples. And so what that means is you have a chemical equation and you're dealing with the heat in or out of it. So first, say we have a physical change. So at 0 degrees Celsius and 1 bar of pressure, ice melts. Okay, you know this, ice melts at 0 Celsius. So measurements show that 6.01 kilojoules of heat are absorbed into the ice for every mole of ice that melts. So we can say that given constant pressure, our heat at constant pressure is equal to delta H, enthalpy. And then, all right, water the solid goes to water the liquid. We can say for this reaction here, the enthalpy change is so many kilojoules per mole. So the per mole here part is important. It says per mole of the reaction as written, you'll get 6.01 kilojoules of heat absorbed because it's the positive number. So like Q, delta H is positive if energy is absorbed, and for ice to melt it needs to absorb energy from the room. Now if it's the other way around, if it's an exothermic process, then delta H is negative, just like Q. So what this means is, if you take the entire reaction here and multiply this by 1 mole, then that is the amount that we refer to when we say a mole of the reaction or process as it's written. Likewise, if you have this reaction down on the bottom, 2A plus 3B goes to C, and you have some delta H value for it, equals something, then when we say 1 mole of the reaction, we mean 2 moles of A, 3 moles of B, and 1 mole of C. Like if you said, I'm going to take 1 mole times all of this. So that's how this delta H value is referenced. It's referenced to 1 mole of the reaction as it's written, which means just multiply the whole thing by 1 mole. And then that's how much stuff you have. 2 moles of A, 3 moles of B, etc. Alright, so second, let's show this for a chemical change. So here you're burning propane in oxygen to make carbon dioxide and water. If you've ever cooked on a barbecue grill or a portable stove, you're probably burning propane. Now, the standard state enthalpy change of this reaction, delta H with the degree sign, subscript Rxn, short for reaction, is equal to negative 2,044 kilojoules per mole. Negative because this is a highly exothermic process. You're cooking something. It's going to release heat. So what this means is if you multiply all of these by 1 mole, is that you have 5 moles of O2, 1 mole of C3H8, 3 moles of carbon dioxide, and 4 moles of water. When you have that amount of reactants and products, you're going to release this amount of heat to the surroundings at constant pressure. Because remember, delta H is heat at constant pressure, so assuming you're running a constant pressure reaction, delta H is heat. There's a reason why the symbol for enthalpy is H. And oftentimes we'll use the word heat when we really should use the word enthalpy, because for many situations it's the same thing. So, looking at this, we can make some ratios that if we look at the delta H reaction for 1 mole of propane, here's this amount of enthalpy change, so this amount of heat released at constant pressure. We can say, all right, for every mole we have this much, or the inverse of that. And then if we look for the oxygen, 5 moles of oxygen releases the same amount of heat at constant pressure. So we can say, all right, this number of kilojoules of heat released over 5 moles of oxygen, or the inverse of that, and so on and so forth. So what we can do with that is problems of this type. Calculate the heat evolved. Evolving in this case means leaving. The heat evolved at constant pressure when 11.7 grams of propane is combusted. All right, so we have the molar mass of propane here. So first, well, we have 11.7 grams of propane. And now we have a relationship between enthalpy, and thus heat released at constant pressure, per mole of propane. So we need to convert from grams to moles of propane. So there's that. And now we're going to use the new piece, and I put it in a different color just to say that it's new. So we release negative 2,044 kilojoules of heat, and we got that number because it's listed in the reaction above. And then that's per 1 mole of propane, because I circled it here. There's a 1 for the stoichiometric coefficient, so that's what we use there. If we were talking about oxygen, then we'd put a 5 there, for example. Okay. Then you just hit enter on your calculator, and you get negative 542 kilojoules of heat are released when this amount of propane is combusted at constant pressure. Alright, so here's another example. Calculate the heat evolved in kilojoules when 24 grams of ammonia are reacted according to the following equation. So first, a pop-up question. Is this going to be negative or positive? Okay, and now let's do the problem. So we start with the 24 grams of ammonia, and then we need to convert that into moles. So here's the conversion to moles. And now we need to use the new bit, the relationship between the enthalpy change for the reaction and the stoichiometric coefficient. So that's 4 moles of ammonia for negative 904 kilojoules. Because we look up here, we have negative 904 kilojoules as the enthalpy change listed. And then we have a coefficient of 4 in front of the ammonia. So those come together to form a new conversion factor that we can now use here. So we put the ammonia on the bottom so it cancels out the moles of ammonia on the left. And then negative 904 on the top. And then you put this in your calculator, and you get negative 318 kilojoules. And there's only 2 sig figs on that, so that's negative 3.2 times 10 to the 2 kilojoules of heat released from this reaction at constant pressure. And so, since there's the degree sign up here in your enthalpy at standard state, that means that this number you calculated is only valid for reactions run at 1 bar of total pressure. Just something I wanted to point out so you can keep that in mind. Alright, that's all we have on enthalpy and thermochemical equations. Thanks for watching.